Hi everyone, in this video segment we are going to be talking about resonance withdrawal effect on acid and base strength. I want to preface this by saying that your professor might literally just say resonance effect on acid base, but I want to distinguish this idea of resonance withdrawal and resonance donation. Electron withdrawal is the pulling of electron density, and electron donation is the pushing towards something else of electron density. Okay? So we're specifically looking at resonance electron withdrawal. And in general, we could say that resonance electron withdrawal in the conjugate base will be indicative of greater acidity in the conjugate acid form. Okay, this is because the resonance withdrawal, the resonance stabilization in the conjugate base provides additional stability to that conjugate base. And that would be then more stable, a conjugate base with the resonance compared to something with either less resonance or no resonance in the conjugate base. Okay, so let's dive into some examples here to illustrate this idea of resonance withdrawal. Okay, resonance stabilization in the conjugate base. We are going to compare water, H2O, to phenol, to a carboxylic acid, acetic acid. Notice the difference in pKa values here. Okay, and the difference in acidity is now a function of the resonance in the conjugate base. So what we're going to do is say, first, each of the atoms bearing the acidic proton are the same. Okay, so it's not going to be a difference in electronegativity or size or necessarily hybridization state that best describes the difference in acidity. It's electronic effects, and here it will be resonance withdrawal. So let's now deprotonate all of those acids and look at the conjugate base. So now we have O minus for each of these atoms, okay, the conjugate base forms. And going from left to right, you'll see increasing conjugate base stability. Now, our far left example, OH minus, that negative charge is isolated, okay? It does not resonate. There's no other electronic force acting to stabilize the negative. The oxygen is on its own stabilizing the negative charge. In our middle example, you have an oxygen atom which is directly bonded to the pi system. It can resonate this negative charge around the ring, and we would create this resonance contributor here, okay, where we are delocalizing the negative charge around the ring across the pi system. Okay, so there is resonance stabilization of the negative charge here. There is not resonance stabilization of the negative charge there. We can view this as the resonance is withdrawing the electron density away from where the negative charge is originating on the oxygen atom, hence why I'm saying resonance withdrawal. All right, now there are additional resonance structures where we could pass this negative around the ring. However, overall, this resonance around the benzene ring is not quite as effective as the resonance in the carboxylate in this anion. When we resonate this negative, we are delocalizing the negative onto the oxygen up top, okay, creating this resonance contributor. And what we notice about these two resonance structures is that they're equal energy. They're essentially the same compound, okay? They are equal energy resonance contributors. We're going to say equal energy resonance structures. And you have two oxygen atoms sharing in that negative charge, right? So here, there's a back and forth of this negative charge between the two oxygens and a very effective stabilization of the negative compared to how the negative is stabilized in either of those first two examples. Yes, when you resonate this negative over the benzene ring, there will be more resonance structures. However, notice how that negative is resonating over carbons. Carbon is less electronegative than oxygen, so it doesn't stabilize the negative as well. In the far right example, you have two oxygens stabilizing the negative charge, as well as the fact that they are equal energy resonance contributors. And if you remember back to the intro series on resonance, we said that resonance stability, the stability afforded to the molecule by virtue of the resonance, was going to be greater if you had either more contributors or the resonance structures were more similar to each other in energy. And what we'll see here is that the resonance is more impactful in the carboxylate when we delocalize over the two oxygen atoms. And accordingly, if this is the most stable anion, the most stable base, that means means it is the weakest base. If this is the weakest base, its conjugate acid is the strongest acid in the series, okay? Now, I really want to stress this idea that here we're looking at resonating the negative charge away from where it is originating, and that resonance is providing stability to the conjugate base. Anything that enables the conjugate base to have more stability licenses the acid to lose its proton more readily. Does that make sense? So that's very important. Anything that provides additional stability to the conjugate base enables the proton in the acid form to come off more readily because we can accommodate that density well. Okay, so here we had resonance in the conjugate base. And what I want to do real quick is just show you how subtle this can be visually. If you looked at this acid versus this acid, we have the proton bonded to the same acidic atom. But when you look at the conjugate bases, I'm going to draw those in red down here. The conjugate base of the first species would have O-. Conjugate base of the second species is this guy. In this structure, there is no resonance. In this structure, there is resonance of the negative charge away from where it originates. Why there is no resonance in this first example is we cannot delocalize the negative charge towards an sp3 hybridized atom. That does not work. There's no p orbital on that atom to help us delocalize that charge. However, in this case, the oxygen atom is directly bonded to the pi system, and therefore we can delocalize. Because there is resonance stabilization of that negative charge, that means that negative charge is more stable. If this is more stable, this is a weaker base. If this is a weaker base, then its conjugate acid is the more acidic acid in that comparison, okay? That's really important. So this acid is a weaker acid than this acid. Stronger acid, weaker acid. And this is the stronger acid because in the conjugate base, there is greater stability, and that is here a function of the resonance of the negative charge away from where it is originating. In another video, we are going to discuss resonance donation, which is the flip side, pushing electron density towards where the negative charge is originating in the conjugate base, okay? But here, taking that negative and resonating it away from where it is originating once our acid is deprotonated, that is stabilizing to the conjugate base, and that will then allow the acid form to be more acidic.